severe weather alert right in the middle of it.
And that alert is centered on our subject for today, Tropical Depression 35W.
Right. And you see it's called a depression, which sounds, I guess, not too threatening. But the path.
The path is incredibly complex, and that's why this is a perfect deep dive. You have this system, 35W, and it's projected to move over some of the most populated areas and busiest shipping lanes in the world.
Okay, so let's unpack this. I want to understand how this one storm is going to affect so many different countries, from the Philippines all the way to Indonesia over just the next few days.
Well, let's start with the here and now. If you look at the data point on the map for today, 6 p.m.
I see it. It's right near Puerto Princesa in the Philippines.
Exactly, and the stats there are key. The wind speed is listed at 48 kilometers per hour.
So 48 kilometers, that's not hurricane force, not by a long shot.
No, it's not a major destructive threat, but it's definitely strong enough to cause problems. You're talking about, localized power outages, serious disruptions for any port facilities in the area. It's not something to ignore.
And what about the pressure? I always hear that's the real indicator of a storm's engine. The map says 29.77 inches of mercury.
That's a critical detail, and the units are important. Most of the world uses millibars, but this source uses NHG. So 29.77, that's about 1,008 millibars.
So what we need to watch is whether that number goes up or down.
Precisely. Lower pressure means a stronger storm. If that number starts to drop, the winds are going to spin up. It's the number we'll be watching most closely.
And what's powering this forecast? What's the tech behind it? The map is very specific. It says the model is ECMWF.
Right, the European model. We often talk about the American GFS model, but many forecasters consider the ECMWF the gold standard, especially for these medium-range forecasts, several days out.
So for you, the listener, knowing it's the ECMWF model is almost like a credibility stamp?
It is. It tells you we're looking at data from one of the most powerful and reliable forecasting engines on the planet. This isn't just a guess. It's a very sophisticated projection.
And it gets even more interesting when you see all the other tools listed on the interface. It's not just a line on a map.
Not at all. You've got weather radar, satellite imagery, rain and thunder forecasts, even wave height and rain accumulation.
It just shows that forecasting it's a synthesis of everything, right? Is how wind, water, and pressure are all interacting in one big system.
That's a perfect way to put it.
Okay, so let's chart the actual path. We've got 5 days of projections here, and this storm's journey looks like a real drama.
It really is.
Yeah.
The first act, if you will, is this immediate slight intensification. So as 35W starts to move west, the model shows that central pressure beginning to drop.
Okay, so by tomorrow morning, what are we looking at?
By tomorrow at 6 a.m., the wind speed ticks up to 52 kilometer raters. And look at the pressure. It drops to 29.74 NHG.
It's a small drop, but it's not insignificant.
Not at all. It confirms the system is organized and it's pulling energy from the warm water it's moving over. It's getting stronger.
And it seems to peak pretty quickly after that. The map shows the single strongest point in the forecast is on Tuesday evening around 9 p.m.
That's the one. The wind speed is predicted to hit 59 kilometer errors, and the pressure holds at that low point of 29.74. That's the storm at its most intense, at least for this 5-day outlook.
And geographically, where is it at that point?
It's moving west, right into the South China Sea, and a nearly 60-kilometer area system in that area. That's a serious threat to some of the world's most critical shipping lanes.
So ports like Da Nang in Vietnam would be watching this very, very closely.
Absolutely. This is where a seemingly small increase in wind speed can create these huge economic and logistical ripple effects. They'd be activating contingency plans for sure.
So we've charted its peak. But what really strikes me looking at this is how quickly it seems to run out of gas after that. The model predicts a really sharp slowdown.
It does. It's fascinating. The energy just seemed to drain right out of it.
Let's look at that midweek point. By Wednesday night, around 10 p.m., the speed has dropped all the way to 39 kilometer.
That's a massive deceleration in just over 24 hours. At that point, it's forecast to be near Bandar Seri Begawan, over in Brunei.
So what does that tell you? Why would it slow down so fast?
It's hitting some kind of unfavorable environment. It could be interacting with land, maybe it's pulling in drier air, or the upper level winds are tearing it apart.
But the pressure is still low.
And that's the interesting part. The pressure is holding at 29.74, but the winds are dropping. It suggests the system is it's struggling to maintain its structure. It still has a low pressure center, but it's losing the ability to spin the air efficiently.
And that weakening trend just continues, right?
It becomes really pronounced. By Thursday at 11 p.m., the speed is down again to 37 kilometer. But here's the key. The pressure starts to rise. It goes back up to 29.77.
Ah, so that's the meteorological signal that it's really falling apart.
Exactly. Higher pressure means the storm is filling in, it's dissipating. At this point, it's near Koeta Baru, close to the Gulf of Thailand.
So the system is winding down, but does that mean the danger is over?
Not at all. The danger just changes, it transforms.
How so?
As the wind energy drops, the threat shifts entirely to water. Look at the forecast for Friday morning at 6 a.m. The speed is at its lowest point in the whole forecast, just 30 kilometer.
Practically nothing in terms of wind. And where is it then?
It's right over the very dense, highly populated area around Kuala Lumpur and Singapore.
Oh, I see. So it's not moving fast. It's just sitting there.
Exactly. It's moving slowly and just dumping all that tropical moisture it collected. The primary threat is no longer wind. It's now a major risk of urban flooding in those huge metro areas.
And then the map gives us one last checkpoint for Saturday at midday.
Right. The speed ticks up a tiny bit to 35 kilometer, probably because it's moved a little bit back over water. But the pressure is the highest in the whole forecast, 29.8 NHG.
And its final resting place, so to speak.
It looks like it's near Banda Aceh in northern Sumatra, Indonesia. Just the remnants at that point.
Wow. So if you connect all those dots, you get this incredibly volatile life cycle.
You really do.
Yeah.
The ECMWF forecast shows a storm that, strengthens off the Philippines. It peaks as a maritime threat in the South China Sea, and then it weakens and transforms into a flood risk for Malaysia, Singapore, and Indonesia.
The sheer geographic scope is just incredible. So let's step back. We've tracked this whole journey. For you, the learner, it's about seeing how those numbers, speed, and pressure tell a story.
And the data gives us this perfect little case study in atmospheric physics. We saw it clearly. The lowest pressure, 29.74 NHG, happened at the exact same time as the highest wind speed, 59 kilometers, on Tuesday.
It's a direct relationship.
It's the fundamental mechanism. The lower the pressure, the stronger the vacuum effect, which pulls air in faster and makes the wind spin harder.
And on the flip side, that pressure rising back up to 29.8 by Saturday is like the storm taking a final breath.
It's the confirmation that the system is disorganized and it's just not capable of producing those damaging winds anymore. It's a key lesson. You should track pressure just as closely as you track the wind speed.
It's amazing to think about the coordination required. You have 2 Gigarao, Puerto Princesa, Da Nang, Singapore, Kuala Lumpur, Banda Aceh, all these places impacted by one system.
It's a logistical nightmare for governments trying to coordinate their response. And that's why this level of detail is so critical.
Which brings us back to the source material itself. The depth of the data in just this one screenshot is how modern meteorology handles that challenge.
I mean, we had 7 distinct timestamp points, specific wind and pressure readings, and the ID of a highly reliable forecast model. That's the kind of depth that lets every region know exactly what kind of threat is coming and when.
So, to sum it all up for everyone listening, the story of Tropical Depression 35W is this dynamic, multinational journey. It has a clear peak intensity on Tuesday before it weakens, but it doesn't just disappear.
Right. It transforms from a wind and wave threat into a really serious rain and flooding concern as it drifts down towards Malaysia and Indonesia.
And that's the big takeaway. This sophisticated data lets people in completely different countries prepare for completely different impacts days in advance.
Which leads to a final thought, something for you to consider.
Mm-hmm.
We saw the storm's energy just collapse between Tuesday and Friday. The wind speed was basically cut in half.
So the question is, why?
Exactly. What fundamental shift in the storm's environment? Was it a patch of cooler ocean water? An intrusion of dry air from the continent? What could cause a tropical system to dissipate so dramatically over just 3 days? That's where the real deep dive into the meteorology begins.